Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Picture Axial Seamount, a massive underwater mountain rising from the Pacific seafloor, suddenly swelling like a balloon as magma fills chambers deep below. This isn't just another restless volcano, it's showing the exact same warning signs that preceded Mount St. Helens. But this time, it is happening beneath millions of gallons of seawater that could turn an eruption into something far more catastrophic. But here's what has oceanographers in full panic mode. The volcano's pressure buildup is accelerating faster than ever recorded, with the seafloor literally rising centimeters every few days. Even more terrifying, the activity is spreading outward along the ridge, triggering earthquake swarms that could unlock the Cascadia Subduction Zone, the sleeping giant that could generate a magnitude 9.0 megaquake. Scientists warn that if Axial erupts suddenly, the shock waves could travel through the ocean crust for hundreds of miles, potentially triggering over 10,000 secondary earthquakes across the Pacific Ring of Fire. The question isn't if this underwater volcano will erupt, it's whether its awakening will be the first domino in a geological catastrophe that reshapes the entire West Coast. So how do we know this isn't just a false alarm? The answer lies in the live data streaming from the deep and the experts sounding the alarm now. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Beneath nearly a mile of Pacific water, a web of cables stretches from the Oregon coast to Axial Seamount, creating a direct link from the ocean floor to research labs on land. This is the Ocean Observatory's initiative's Regional Cabled Array, a technological feat that delivers a real-time feed of seismic, pressure, temperature, and chemical data. More than 140 instruments are stationed across Axial's summit and flanks, each one designed to capture the subtlest changes in the volcano's behavior. Bottom pressure recorders, accurate to fractions of a millimeter, track the slow rise and fall of the seafloor as magma moves below. Seismometers pick up the faintest tremors, distinguishing between distant earthquakes, local microseismicity, and the shudder of magma pulses. Hydrophones record the low rumbles and sharp cracks that signal shifting rock and boiling fluids. Underwater cameras positioned near hydrothermal vents stream images of mineral towers and shimmering water, offering a window into the volcano's constantly changing world. William Chadwick, a leading volcanologist at Oregon State University, describes the system as a revolution in how scientists watch the seafloor. He and his team can access data collected minutes earlier, allowing them to spot anomalies as they happen. Jeff Beeson, the geologist responsible for maintaining the pressure recorders, explains that each instrument is calibrated to detect changes smaller than the thickness of a sheet of paper. This level of precision means scientists are not relying on guesswork or sporadic ship visits. They have a live, unbroken record of every movement, every pressure change, and every signal from deep within the volcano. The result is a level of situational awareness once thought impossible for such a remote and hostile environment. With this infrastructure in place, researchers are prepared to interpret Axial's every signal, no matter how subtle or sudden. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Pressure readings from Axial Seamount have captured a pattern that stands out from decades of careful observation. Since the start of October 2025, the rate of seafloor uplift has accelerated beyond anything recorded since the network of sensors was first deployed. Where typical inflation cycles measured just a few millimeters each month, recent data show the summit rising by several centimeters every week. This is not a subtle trend. Researchers are tracking a vertical displacement that rivals the buildup before the 2015 eruption, but compressed into a fraction of the time. William Chadwick, leading the Oregon State team, describes the numbers as both astonishing and deeply concerning. The caldera's floor, once stable, now swells at 3 times the rate seen a year ago. On some days, the pressure recorders log more than 1 centimeter of uplift in just 48 hours. These changes are not isolated to a single spot. The deformation stretches across the summit and down the volcano's flanks, signaling that magma is pushing into the shallow reservoirs with unusual force. This rapid inflation is not just a record on a graph. It means that the main magma chamber, already one of the largest known beneath any submarine volcano, is approaching the mechanical limits that have triggered eruptions in the past. The pressure buildup is so pronounced that even seasoned researchers admit they have never seen the system respond this quickly. Each new pressure spike adds urgency to the monitoring effort, as the risk of a sudden breach grows with every passing day. The data leave little doubt. Axial's magma system is under stress, and the next stage could arrive with little warning. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Hundreds of tiny earthquakes now rattle the crust beneath Axial Seamount every day. These microquakes, too small to be felt but unmistakable on seismometer records, form an unbroken drumbeat across the summit and down the volcano's flanks. Their energy signatures tell a story of rock fracturing and magma pushing its way upward, cracking open new pathways as pressure mounts below. The frequency and pattern of these quakes have shifted. Instead of staying clustered near the caldera, seismic activity is migrating outward along the Juan de Fuca Ridge, evidence that the stress is no longer confined, but spreading through the crust. NOAA geophysicists tracking the data described the current swarm as the most persistent since the months leading up to the 2015 eruption. On some days, the network logs more than 1,000 events, each one a mechanical response to magma forcing its way through brittle rock. Spectral analysis of the seismic waves reveals low-frequency tremors mixed with sharp, brittle failure quakes, a combination that points to both slow magma movement and sudden rock breakage. The multi-sensor confirmation is clear. Microseismicity is not random noise, but a direct signal of magma migration. As the swarm grows, the pattern matches what scientists expect when the volcano's plumbing system is under pressure. Every spike in quake counts is cross-checked with pressure and deformation data, building a picture of crustal stress approaching its limits. The outward spread of these quakes suggests that the mechanical response of the volcano is accelerating, with fractures propagating away from the summit. For researchers watching these numbers, each new day of seismic unrest adds urgency to the question: how much more stress can Axial's crust absorb before it gives way? Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Heat rising from the summit of Axial Seamount is now setting new records, confirmed by satellite sensors tracking thermal emissions across the Northeast Pacific. These maps show a broadening patch of elevated heat flow, with values exceeding anything measured since the first deep-sea surveys in the 1990s. The ocean floor above Axial is no longer just warm, it is radiating energy at a rate that signals something is stirring below. At the same time, the chemistry of the hydrothermal vents is shifting in ways that only occur when magma is on the move. Water samples collected from the Ashes and International District vent fields are returning with a sharp spike in dissolved helium-3, a rare isotope that escapes from the mantle only during active magma intrusion. Ratios of sulfur, iron, and manganese are also climbing, marking the arrival of fresh volcanic gases and superheated fluids from new cracks in the crust. The changing chemistry is a clear signal of subsurface activity. Dr. Lena Hofstadter, a vent chemist from Germany's Geomar-Helmholtz Center, has spent years analyzing Axial's hydrothermal outputs. She describes the latest results as unmistakable. Helium-3 levels are now 3 times higher than baseline levels, and the sulfur signature matches what was seen in the weeks before the 2015 eruption. These changes can only be explained by a surge of hot, volatile-rich magma rising from deep reservoirs and forcing its way upward. The vent fields themselves are responding. Underwater cameras have recorded dense clouds of shimmering water, a sure sign of superheated fluids mixing with cold seawater. Some vent chimneys that were once steady now pulse with bursts of steam and gas, and their mineral deposits are growing at accelerated rates. All of this points to a system under stress, one where the heat and chemistry of the ocean itself are confirming what the instruments have already shown. Magma is rising, and the volcano's inner workings are heating up faster than at any time in the last decade. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Computer models built by geophysicists at the Pacific Northwest Seismic Network now process real-time data from Axial Seamount alongside seismic records from across the Pacific. These models use principles of Coulomb stress transfer, which track how changes in pressure at one fault or volcano can subtly alter the stress on others, sometimes thousands of kilometers away. The idea is not new. Seismologists have long debated whether one major event can nudge distant faults closer to failure. In 1960, the massive Chilean earthquake sent stress ripples through the Earth's crust, coinciding with a flurry of large earthquakes in Japan, Alaska, and the Philippines over the following year. Today's networked sensors and supercomputers allow scientists to watch these stress migrations in near real time, mapping how energy released at one point can raise the odds of activity elsewhere. Recent months have seen a troubling uptick in volcanic tremor and earthquake swarms, not just at Axial, but along the Kuril Islands, the southern coast of Chile, and the Philippine Trench. Analysts at the USGS and the Japan Meteorological Agency have compared these patterns, noting that the timing and frequency of quakes appear more clustered than random chance would predict. The question is whether these are isolated coincidences or subtle evidence of a global synchronization. While no single event at Axial could instantly trigger a distant megaquake, the models show that even small shifts in crustal stress can accumulate, especially in regions already near their breaking point. Stress model specialists like Dr. Maya Tolstoy emphasize that the Earth's tectonic plates are not isolated systems. Each movement, each magma surge, sends out pressure waves that can be detected far beyond their source. The current wave of activity across the Ring of Fire is being watched with new urgency, as the possibility of remote triggering once considered unlikely gains traction in the scientific community. The stakes are clear. A pattern of synchronized unrest could mean that a single underwater eruption, under the right conditions, might set off a chain reaction affecting entire continents. For scientists, the challenge is not just to monitor what happens at Axial, but to understand how its every pulse could echo across the planet's most volatile fault lines. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. When an underwater volcano like Axial Seamount erupts, the threat to coastal communities isn't just from lava or ash, it is from water itself. If a powerful eruption or a sudden collapse of the seafloor triggers a submarine landslide, a wall of water can form and race outward at highway speeds. Unlike tsunamis from distant earthquakes, which can take hours to reach land, a wave generated just 300 miles offshore could arrive in under 20 minutes. Along the Oregon and Washington coasts, that leaves little time for emergency alerts or organized evacuations. In some low-lying towns, The first warning might be the sudden retreat of the tide, followed by a surge that overtops seawalls and floods streets. Emergency planners have run the numbers. For many coastal neighborhoods, the window to reach higher ground is measured in minutes, not hours. Sirens, text alerts, and evacuation routes are all designed with the hope that people can move fast enough. But in a worst-case scenario, the margin for survival is razor thin. The reality is sobering. When the threat comes from the ocean floor itself, every second counts. The Pacific Northwest is not just a coastline of small towns and scenic beaches. It is a critical economic corridor linking the United States and Canada to global markets. Over 10 million people live in the urban arcs, stretching from Portland to Seattle and Vancouver. At the heart of this region are deepwater ports like Seattle, Tacoma, and Portland, which move more than $80 billion in cargo each year, everything from Asian electronics to Midwest grain. These ports are lifelines for the tech sector, agriculture, and manufacturing, with supply chains reaching across the Pacific and deep into North America. The stakes go beyond shipping containers. Seattle's tech industry, Portland's silicon foundries, and Vancouver's logistics hubs all depend on uninterrupted access to power, data, and transportation. Yet insurance industry analysts warn that a major disruption, whether from seismic shaking, landslide, or port closure, could ripple through the global economy. Many policies exclude losses from volcanic or seismic events, leaving companies exposed to billions in uninsured risk. As scientists debate the likelihood and timing of the next eruption, business leaders and public officials are forced to weigh the real-world costs of a region perched on the edge of geological uncertainty. Oregon's underwater volcano is awakening, and scientists are issuing a megaquake warning because what's happening 480 kilometers off the Oregon coast could trigger the most devastating chain reaction the Pacific Northwest has ever seen. Eruption forecasts at Axial Seamount remain a source of spirited debate among scientists, with teams from the United States, Japan, and Europe comparing real-time data and refining models in parallel. Some researchers point to the volcano's current state, fully reinflated, but with inflation rates slower than in the past, as evidence that an eruption could still be months away. Others argue that subtle changes in seismic noise or vent chemistry could signal a much shorter timeline, perhaps just weeks. The uncertainty is not just about data interpretation, but about the very nature of volcanic systems that rarely follow a script. Adding to the complexity, the current solar maximum has prompted a new round of discussion. Solar physicists and geophysicists are examining possible links between heightened solar activity and increased tectonic stress, analyzing whether fluctuations in the Earth's magnetic field could nudge volcanic or seismic systems closer to failure. While the evidence is far from conclusive, the timing has led to a surge in collaborative studies, with multinational teams sharing sensor data and cross-referencing eruption timelines with solar flare records. International monitoring protocols now require near-instant sharing of seismic and pressure data, with research vessels from several countries coordinating their deployments across the Northeast Pacific. For every model that predicts a sudden eruption, there is another urging caution, and for every confident forecast, a reminder of the system's unpredictability. The world's best instruments deliver clarity, but not certainty, leaving scientists and everyone watching suspended between anticipation and doubt. Right now, over 10 million lives and the backbone of the Pacific Northwest economy sit in the shadow of a restless seafloor. As real-time data pulses from the ocean depths, emergency plans and scientific debate cannot outpace nature's timeline. Preparedness is not an option, it is a necessity. In a world wired to the edge, tomorrow's warning may leave no time to act. Let us know your thoughts in the comments below. Alaska's 6.0 earthquake just shocked scientists on Thanksgiving morning. And what's coming next is absolutely terrifying, because this quake follows the exact same pattern that preceded history's most devastating megaquakes. Picture 300,000 people in Anchorage waking up to violent shaking at 6 a.m. on Thanksgiving Day, their homes rattling, dishes crashing to the floor, and the ground beneath their feet betraying them without warning. But this magnitude 6 event is not just another Alaska earthquake. It is happening after 17 days of complete seismic silence, a geological calm that scientists now realize was the Earth holding its breath. Here is what has seismologists in full panic mode. There is a 5% chance this earthquake is actually a foreshock to something much bigger. The same stress patterns, the same location, the same warning signs that appeared before Alaska's catastrophic 1964 magnitude 9.2 megaquake that killed 131 people and triggered tsunamis across the Pacific. But the most chilling discovery came from space weather data. This earthquake struck during the exact same solar conditions that have triggered every major quake in recent history. The timing is not coincidence, it is a cosmic alarm bell. Is Alaska's Thanksgiving earthquake just a one-time jolt, or the opening act of a magnitude 9+ megaquake that could devastate the most populated city in America's largest state? The official story says it was a routine event, but the facts suggest something far more dangerous may be brewing beneath Alaska, and the next few weeks could change everything we know about earthquakes. At 8:11 in the morning on November 27, 2025, seismic instruments across south-central Alaska registered a magnitude 6.0 earthquake. The epicenter was calculated at approximately 14 kilometers west-northwest of Susitna, a rural area about 65 miles from the heart of Anchorage. The event originated at a depth of 80.4 kilometers beneath the surface, placing the source deep within the Earth's crust, far below the reach of most shallow tremors that typically rattle the region. This depth, while significant, meant that the energy radiated outward in all directions, with surface shaking felt across a wide area. The precise coordinates, confirmed by the United States Geological Survey, marked the epicenter at 61.6 degrees north latitude and 150.9 degrees west longitude. These numbers pinpoint a stretch of rugged Alaskan wilderness, but the effects extended well beyond the immediate vicinity. Seismic waves raced outward, reaching Anchorage within seconds. The timing, Thanksgiving morning with many residents just beginning their day, meant that the sudden jolt caught people off guard, though the hour was later than the earliest risers might expect. This earthquake was the largest to strike south-central Alaska since 2021, standing out in a region accustomed to frequent seismic activity. Alaska records more earthquakes than any other state, but a magnitude 6.0 event still commands attention from scientists and emergency planners alike. The Alaska Earthquake Center's network of monitoring stations captured the event in real time, logging the moment the fault ruptured and tracking the propagation of energy through the crust. While the quake's epicenter lay in a sparsely populated area, the seismic footprint covered a vast stretch of the state, setting the stage for a careful assessment of potential damage and aftershocks. Damage reports from Anchorage and surrounding communities arrived quickly. Emergency services canvassed neighborhoods, checking for collapsed structures, gas leaks, and injuries. The initial sweep found little more than scattered items, cracked drywall, and the occasional toppled chimney. No building suffered major structural failure. Utility crews inspected power lines and water mains, but found only minor disruptions. Anchorage's hospitals remained fully operational, and schools, though shaken, reported no injuries among early staff arrivals. The Alaska Earthquake Center confirmed that a tsunami was not generated by the event. The depth of the quake, nearly 80 kilometers below the surface, meant the energy dissipated before it could displace ocean water or trigger dangerous landslides along the coastline.